Okay, so before moving on to the practical aspect, we do a little review of the two approaches, and we do also explain how the validation of these approaches works. So the first one is the hotspot stress approach, which basically consists in extracting the stress values in certain reference points, and then calculating the stress at the hotspot, so the well toe, by doing a linear regression of the data. The reference points in which the distance of the reference points within with respect to the hotspot, with respect to the well toe, it strictly depends on what type of hotspot stress we want to extract and on the quality of the mesh of our finite element model. It's not working. It's not working. Okay. Okay. Now it works. Okay. Ma io clicco qua, non funziona bene. Okay. Okay, so okay, so if we're doing a fatigue assessment, the hotspot stress associated to a certain cyclic load is equal to the difference between the hotspot stress evaluated at maximum load and the hotspot stress evaluated at minimum load. Once acquired, all the hotspot stress and their corresponding number of cycles to failure are compared with the steel fat curves proposed by the IIW to see if the data matches the fatigue design curve suggested by the IIW itself. For example, in our case, for T-welded joints, the IIW suggests to use a curve, the FAT 70 curve, FAT 71 curve, or FAT 80. It's not working. Okay, now it works. It's quite bizarre, but okay. So moving on to the second approach, that is the strain energy density approach. I think Dr. Fodi explained really well how it works. I repeat. So brittle failure, this approach is based on the idea that brittle failure will occur in a small control volume with a certain radius when the strain energy density associated to that control volume reaches a critical value. And for our case, for a V notch with a toe angle of 135 degrees, so we assure that the non-singularity of mode 2, so we had just mode 1 crack opening propagation. The control radius, which depends on the, as I said, the crack propagation mode and on the material, it's given by the formula reported here. Okay. How do we do the assessment? With finite element analysis, we can calculate the strain energy density associated to the control volume by doing the ratio between the deformation energy associated to the volume and the volume itself. The assessment is done by, the validation is done by comparing all the values obtained by, the strain energy density values obtained by plotting them alongside the scatter band. That these are the strain energy density curves for fatigue. These one in particular were proposed by Olivieri and Lazzarin, and were made with a bulk of over 900 fatigue data. So there is the mouse pointer here. Okay, so moving on to the setup. This is the setup that was proposed by Taylor and then replicated by Corigliano for titanium joints. The lower plate is basically clamped with 2 bolts, and the vertical plate is loaded with another clamp. As we said before, in both cases we're dealing with toe angles of 135 degrees, so we assure mode 1 crack propagation at the well toe. Moving on to the finite element analysis model that we created, it's a completely parametric geometry, and it was used to assess both the hotspot stress and the strain energy density values. As we can, symmetry was applied in order to save also time and computational resources. As we can see, the model is divided into 3 areas. The area framed in red was created in order to favor a smoother transition between the mesh within the control volume that is framed in black, and the rest of the mesh that is auto-meshed. As for the control radius value, the one for steel is nowadays well assessed, well consolidated, was evaluated by Livieri and Lazzarin. The second one for titanium was evaluated by Meneghetti, but it refers to the base material, not the welded one. Moving on to the steel joint, these are the data from Professor Taylor. The load applied was the load was applied with a load ratio of 0.1. Okay, so this is a comparison between the hotspot stress values and also, as we can see, the hotspot stress follows really well the trend set by the experimental one. Moving on to the validation of the hotspot stress method, if we plot the hotspot stress values along with the steel fat curves proposed by the IIW, we see that for the first 200,000 cycle around, the values are really well described by the FAT 80 curves. While moving on to higher number of cycles to failure, we see that there is a little scatter of the data, but it is still okay because, as we said, the IIW suggested to use FAT 80 as a design curve for fatigue. So using the IIW approach is safe, even if it is still a bit conservative. Moving on to the validation of the strain energy density model, we see that if we plot the strain energy density values for each fatigue load along with the scatter band proposed by Livieri and Lazzarin, we see that they fall within the scatter band, and even if the lower values fall within the lower line of the scatter. So it is safe to design using this approach, using obviously the curve that guarantees the highest chances of survivability. Moving on to okay. Moving on to the titanium joints, these are the experimental values proposed by Corigliano, again with a load ratio of 0.1. There is okay. Here again there is a plot. We are confronting the hotspot stress values with the experimental loads, and we see that the data follow the trend really well. As for the validation of the hotspot stress method, the IIW curves that we've seen before are stress range based curves. So we cannot compare the stresses that comes from titanium with the stress related to steel, because their mechanical response to external loads is completely different. So a preliminary approach suggested by Corigliano is to normalize the fat curves with respect to the steel Young modulus. So we're comparing strains now and not more stresses. And if we compare the new normalized fat curves with the hotspot strain that we obtained from finite element analysis, we see that the data falls in between the FAT 100 curve and the FAT 150. And as we said before, the IIW suggests a conservative approach. So in this case, even if it still requires a little further attention, it seems to work. Moving on to the validation of the strain energy density method for titanium, this scatter band proposed by Meneghetti is, as for the control radius that we've seen before, relates to the base material, not the welded one. In fact, we see that the strain energy density values fall completely off the scatter band. So it is not reliable to design with this approach. So if we want to summarize everything, because there was a little bit of confusion before, so we validated for the steel welded joints the two methods, the hotspot stress approach and the strain energy density approach, which is nothing new, but it's still a thing. And we also tried to validate these two methods for the titanium joints. And we saw that for the hotspot stress approach, we got an encouraging result. It's kind of interesting by normalizing the steel fat curves. But as I said before, it requires further attention. While the For the strain energy density methods, we saw that the data falls completely off the scatter band proposed by Meneghetti for the base material. So an experimental campaign is required to, in order to find the proper control radius for the welded material, in order to find the scatter band, the new scatter band for the titanium, for the welded titanium. Okay, that's it. Thank you.